Okay, so this is chapter 1 of the geometry textbook. In this video, we're going to be talking about inductive reasoning. So, inductive reasoning is the process of observing data, recognizing patterns, and making generalizations from your observations, or in simpler words, using reason to make conclusions based on what you see. And this is not to be confused with deductive reasoning, which is the opposite, making specific claims based on general knowledge. Okay, so a bit of vocab. A conjecture is going to be really important in this chapter. That means the generalization that is made with inductive reasoning. So some problems require inductive reasoning. You might have a set of numbers such as 2, 4, 7, and 11 and be asked to find the next two terms. So here we can see that the terms first increase by 2, then by 3, then by 4. So we can see a pattern here. The next term will increase by 5, so that'll be 16, and the next term will increase by 6, and that'll be 22. So here, another example, we could do 1, 10, 100, and 1,000, and then what would be the next two terms. So we can see that each time this is going to be times 10, times 10, times 10. So then this pattern is going to keep going. Times 10 would make 10,000, and then times 10 again, this would be 100,000. Okay, and a different example could be 0, 3, 8, 15, 24, 35. And then looking for the next two, you can see that this increases by 3, then by 5, then by 7, then by 9, and then by 11. So the next term is going to increase by 13 following this pattern, and that will be 48, and then the next by 15, and if we do some addition here, that will be 63. So we could also have a slightly different type of pattern where you still need to use inductive reasoning to find a pattern and then to find the next terms. Now here it might look like it would be easier just to use a calculator to find the value, but that's really not the point of this. It's really not what we're looking for. And the point is that you don't need a calculator because you can recognize this pattern. So here we can see that the innermost digit keeps going up by 1 and then going back down. So with that, we can then see that the next term will be continuing this pattern and will come out to be this. So now we've looked at some patterns that use numbers, and we can move on to some that use pictures. So here's a pattern of dots, and we can find the next two terms by observing the pattern. So what you can see is that in the first one there's one dot, then there's 3 dots, and they're in a triangle pattern. So at each level, each time there's a new level with one more dot than the previous level. So we can use this pattern to then go on and say, if the previous base level had 3 dots, then the next one's going to have 4 dots. And then if the previous one had 4 dots, the next one will have 5. And in this way we're using inductive reasoning to find the pattern. So this next pattern has two sort of things to think about It has the number of dots, which is a pretty clear pattern. It adds 1 each time. And then it has the number of sides of the polygon, which here you can see is going to be 3. And then here it's 4, and here it's 5. So then this is going to keep adding. So our next figure we can now see is going to be a hexagon with 6 sides. And then since the dots also keep adding, we're going to have 4 dots here. So the next part of this lesson is about finding the nth term, n being a variable that can represent any number. So some vocab. A function is going to be a sort of rule by which you can define a pattern, like, for example, add 3 each time, or multiply by -1 each time. So to do these next problems, it's really useful to create a table where you have the n, or the term number, and then the value, which also can be the rule or the function. So here's an example problem. So to do this problem, we want to see what function or rule will make all of the statements above true. So if we go through, we can see that each one adds 4. Every time you go and you add 4. So we can easily find the next term, which would be 35, but how about the 20th or the 200th even? So to do this, we need to find a rule that we can then plug n in to find any term. So we want to find what works for n. We know that there are 4 between every term, so we probably have to multiply 4 by n every time. But it's not quite that simple. We know that the first term is 3, so that means that we have to do something else too. So see, if we subtract 1, then it works. See, if we have n as 1, then we can plug n in here, and that'll be 4 times 1 minus 1, and that equals 3. So that works for the first one. And let's see if it works for the second one. We have 4 times 2, because here n is 2, minus 1, and that equals 8 minus 1, which equals 7. So that works too. So if we go through, we can see that this will work for all of these. So now we know that our n is 4n minus 1, and now we can use that to find number 20. So that will be 4 times 20 minus 1, which is 80 minus 1, or 79. So now, without having to do every term until 20, we could just find the nth term and then use that to find any term we would like. So when the difference between all of the values is constant, like it was for the last example, we have what's called a linear sequence. And it's called linear because if you were to plot all of the values on a graph, it would form a straight line. Okay, so another example that we can do, if you have the n and you have the rule, then you can go through and figure out each term. We can even go to 20 or 200 with this pretty easily. So here we can see that that would be 3 times 1 minus 5. 3 minus 5, that equals -2. And we can go through, and this is going to be 3 times 2 minus 5 equals 1. And then that's going to be 4. This is going to be 7, and you can see the pattern. It's going to add 3 every time because of this multiplied by 3. So you really, once you get the hang of it, if you're just going in order, then you can add 3 every time. Now for a term like 20 or 200, we need to plug it in again. So 3 times 20 minus 5, that comes out to 60 minus 5, which is 55. And then for 200, 3 times 200 minus 5 is 600 minus 5, or 595. So this next section talks about figurate numbers, which are numbers that correspond to geometric figures. The most common being 1, 4, 9, 16, numbers that you're probably more familiar with as 1 squared, 2 squared, 3 squared, 4 squared, etc. And the nth term of this sequence is going to be n squared. And the way that this corresponds to geometric figures is that these are square numbers, so if you line them up, they form squares. And there also exist rectangular numbers as well as triangular numbers, but we won't get into that. So for some figurate numbers, their sequences are more complex and actually form what we call quadratic sequences, which are named because they form quadratic graphs, which look something like that. And they can be a bit more complex to figure out, but it still helps to make a table. If we have a pattern, something like this, and we still need to find the nth term and the 20th term. It's slightly more complex because you can't just, it won't be a constant term that's added. So we can see here is added 6, but then here 8, here 10, here 12, and here 14. So we could still find the next term fairly easily. You would add 16, and that would be 70. But to find the 20th term and the nth term is a little more complex. So what you need to do, you can find the second difference, which is going to be 2 each time. And then what a really good technique is to take these numbers and factor them. So if we go here and we rewrite our table really fast, we can factor these numbers. So this is going to be 1 times 4, 2 times 5, 3 times 6, 4 times 7, 5 times 8, and 6 times 9. So doing that makes the pattern a lot more clear, because we can see that for the first factor here, we're just adding 1 every time. And then we're actually doing the same thing for the second factor, only it starts later. It starts at 4 instead of 1. So, and we can see that these always match. So the first term is going to be the same as n, while the second term is going to be, as we can see here, there's a difference of 3, 3, 3, so it's going to be n plus 3. So now we've found our nth term. Now it's going to be much easier to find our 20th term. So what we do, since n is going to be 20, it's going to be 20 times 20 plus 3, which comes out to be 460. So mathematical modeling, which is the next section, is when you have graphs or pictures describing situations or equations. So, for example, a problem you might get is something like this, and what we want to do is we still want to draw our little chart because that's still going to be really helpful, but we want to do, so it's asking how many diagonals can you draw from one vertex in a polygon with 35 sides. So we really are dealing with the diagonals and the sides. So here are, instead of n, we're going to have number of sides, and then instead of value, we're going to have number of diagonals. So obviously you can't have a polygon with either 1 or 2 sides, but we can start from 3, which is going to be a triangle. We can then go to 4, a rectangle or a quadrilateral, 5, a pentagon, and we can go to 6, which is going to be a hexagon. And then hopefully by that time we can find our pattern and go to 35. Okay, so a diagonal is a line that's drawn from one vertex to another non-adjacent vertex. So this is not a diagonal, but this is. So a triangle actually has 0. Here a quadrilateral has 1 from a single vertex. A pentagon has 2, and a hexagon has 3. So it's a pretty clear pattern here that we can see. So obviously it's going to be adding 1 each time. So we're just going to have n, because this is going to be, the coefficient is going to be 1. But then it's going to actually be n minus 3, because that is what will make this work each time. So then for 35, there are going to be 32 possible diagonals that you can draw. And that's really it for chapter 1. We covered inductive reasoning, as well as how that applies to both number patterns and picture patterns. And then we covered how to find the nth term in both linear and quadratic sequences. And we covered some mathematical models, which is where you really apply these skills to real-life situations.